Hello all, here's a video description for the solution to the grouper called Wagons Roped Together. And so the problem gives us three separate little bike ideas, like a wagon or a big wheel or a tricycle. It says they're all tied together. They each have their own masses, which is listed in the problem. And it says that this whole system is pulled with a force of 22 newtons. And so here's a diagram of the system. So again, this is we call this a functional diagram. And so you label the masses for each object that are given. It tells us that this is tension 1 and that this is tension 2. And then the questions that follow are all related. So because the bike and, because all three objects are tied together, they're tied together with a rope. That means that they're all going to accelerate at the same rate. So the acceleration for all three should be equal. The way to find acceleration is to recognize Newton's second law says that the net force applied will be equal to the mass times the acceleration. So you can solve for acceleration by rearranging this equation to show that acceleration equals the net force divided by the mass. Now the whole thing, if you treat it all as one system, the whole thing has a mass of 77 kilograms. So if you pull with 22 newtons on 77 kilograms, the acceleration of all three of those objects together as one system will be 0.286 meters per second squared. Now, to solve for the tension here between the red wagon and the big wheel, it's really helpful if you do the free body diagrams for each separate object. So now we're splitting this system apart. If you look at only the red wagon as your system, the forces acting on it are gravity and the normal force, and it doesn't tell us anything that would make us not make these equal. So on Earth, a red wagon sitting on the surface of the Earth would have the force of gravity down, but then if it's sitting on the surface, it would have the normal force up. But because this red wagon has a string attached to it, or a rope, the only force that it experiences in the horizontal direction is the force of tension, and we call that T1. If you look at the big wheel has two tensions acting on it. It has the tension between the tricycle and the big wheel. That's called T2 from the situation. And it has the tension between the red wagon and the big wheel. That was called T1 from the problem. So the big wheel has four forces. Oh, we could probably mark that the gravity and normal forces are equal. But the question to answer the tension between the wagon and the big wheel, you need to recognize that this tension is equal to this tension. These two objects are pulling on the same rope. They're going to pull with the same force. That's what Newton's third law says. So Newton's second law right here, F net equals ma. Newton's third law is action-reaction. If you pull this hard on the rope, if you pull on the same rope, then the force is equal, but opposite. So the question to solve for the tension between the red wagon and big wheel is easier if you look at this part of the system, because you know that the force of tension is the only unbalanced force. And so now you can relate the tension to the net force. So here's the statement that's really important. There's two ways to talk about net force. The net force is the sum of all of the forces, and then also it is the mass times the acceleration. And so in this case, the sum of the forces is just Ft1. If you add all of the forces together, the only remaining unbalanced force will be Ft1. And so, acting on the red wagon, the tension that is necessary to cause 36 kilograms to accelerate at 0.286 is 10.3 newtons. So if I could put a little line right here. All of that is to the problem above. Okay, and then question 5 asks you to determine the tension between the tricycle and the big wheel. So now we can look at the FT1, which we know the value for this one, FT1 was 10.3 because it's equal to the FT1 from the red wagon. So the big wheel has normal and gravity, which are equal but opposite. But we know that FT2 must be larger than FT1 because the whole system is accelerating to the right. And so the net force acting on the big wheel must also be to the right. But there are two forces. You have a force to the right and a force to the left. So the sum of all of the forces is going to be equal to two separate things. It's going to be equal to the net force, which is m times a, or it's going to equal to the net force of the sum of the forces. So we know that the net force is 4 newtons. Here's the mass, here's the acceleration. So the net force has got to be equal to 10.3 plus, well, sorry, this is a negative value because it's to the left. So the net force is equal to the sum of the two forces. If the net force was 4, based on this calculation, mass times acceleration, the two forces added together are FT2 and negative 10.3. So if you add 10.3 to both sides to get FT2 alone, the force of tension here must be 14.3 newtons. And so then for the big wheel, you can use these values to draw a free body diagram. You get the normal force up, gravity down, tension to the right, tension to the left, and you can even identify the value of the forces. On the next page, it asks how would it change if it was applied to in the other direction. Now, the acceleration of the system would be the same. That doesn't change. You still have the same force being applied to the same system, and all three of these added together. However, the tension afterwards will be different because the masses and the distribution of the masses are different than they were at the beginning. So consider this relationship. You know that the acceleration is constant. This value can't change. If A doesn't change, but the mass goes up, the force also has to go up. In order for this ratio to stay true, and this is Newton's second law, if a number in the denominator increases, then the number in the numerator increases. So I'm using this notation to show the tension after this change. So like if you pull it the other way, I'm calling T1 prime the tension after the change in direction. And this is T2 prime. Previously we had T1 and then T2. Now we have T1 prime and T2 prime. They're in the same place, but you can see that the mass of the red wagon, big wheel, and tricycles don't change. But when the pull force of 22 newtons is to the left, the tension at T2 prime is now only pulling 27 kilograms. Previously, when you were pulling with 22 newtons to the right, this tension is only pulling 36 kilograms. So overall, the largest tension had to be tension 2 before the pull was changed. Because if you're pulling to the right, that means tension 2 without the little symbol, this little apostrophe is called prime. Without the pull, in the before situation, you have 50 kilograms that are being accelerated by this tension. 36 and 40. 14 is 50. In this direction, you only have 41 kilograms. T1 prime is accelerating both of these objects to the left, and the total mass of those two is 41 kilograms. Then pulling to the right, 36 kilograms is larger than if this was pulling to the left, than 27 kilograms. So T2 prime is the least force because it has the least mass. And this is the ratio you need to understand. If the acceleration is constant, if the mass goes down, the force has to go down. If the mass goes up, force goes up. The last question asks, how would this be different if these were pushed instead of pulled? So none of the values would change. This would be a good demonstration of the third law. So all of the values would be the same, but we're not pulling with a rope anymore. Now we're pushing. And you could talk about each object's effect on another one using this notation. The push on the big wheel by the red wagon would be equal to the push on the red wagon by the big wheel. So overall, instead of tension forces canceling out, now in this case they would be contact forces. This push to the right by the, sorry, I don't have my Apple Pencil. This push to the right by the red wagon would be equal to but opposite of the push back from the big wheel. And then similarly, the big wheel on the tricycle would be equal to but opposite the tricycle on the big wheel. Okay, that's the solution for the group work of Wagons Roped Together. Good luck studying for your quiz.